Dear student, I am Varun Kumar, Assistant Professor Ajay Kumar Garg Engineering College, Ghaziabad. And today we are going to discuss a topic which is algebraic structure in discrete structure and theory of logic. So we are going to discuss what is algebraic structure. Algebraic structure consists of two things. One is the G and another is the asterisk. G is a non-empty set of elements and asterisk is a binary operation on the element of the set. And after that we have checked the behavior of the element of data structure, algebraic structure in this. Okay, it can be follow any of these properties: closure, associative, identity, inverse and commutative. Let's discuss one by one each and every property. That is binary operation on set. If we have set G like this, 1 minus 1 I and minus I. And what is I? I is a square root unity. It means if we put I square, that is equal to minus 1. So here we take binary operation multiplication. So we have to calculate that A asterisk B must belongs to the G. This is the closure property which is said that every pair of element of this particular set, after performing the binary operation, the result must be belongs to the set. So we perform that dot 1 that become 1 dot minus 1 that become minus 1, and 1 multiplied by I, that is I, and 1 multiplied by minus I, that become minus I. And similarly minus 1 multiplied by 1, that is minus 1, and minus 1 multiplied by minus 1, that is 1, and 1 minus 1 multiplied by I, that is minus I, and minus 1 multiplied by minus I, that become I. Minus minus plus, then it will become I. And if we multiply I with the 1, that result is I, and I multiplied by minus 1, that become minus I, and I multiplied by I, that become I square. I dot I become I square, and we know that I square is equal to minus 1. So minus 1 is here, and I dot minus I, that is minus I square, that I multiply by minus I, that become minus I square, and I square become minus 1. So minus 1 dot minus I square, that minus 1, and minus 1, that become 1. So result is 1. Minus I multiplied by 1, that is minus I, then minus I multiplied by I, that is I, and minus I again minus I multiplied by I, that is 1, and minus I multiplied by minus I, that become plus ka I square, which is become to minus 1. So we can say that all product of two element is belongs to this particular set. So this particular algebraic structure, it means this particular all element under this binary operation is closed if our result is belongs to this set only. And second property, we check that another numerical, that what is omega? Omega is cube root unity, that if we multiply 1 by 1, that is 1 by omega, that is omega, then 1 into omega square, that it become omega square, then omega multiplied by 1, that is omega, then omega square, then omega ki power 3, we know that omega ki power 3, that become 1, again omega square, that 1, that is omega square, that omega ki power 3, that become 1, then omega square dot omega square dot omega square, that become omega ki power 4, that we can write this omega cube dot omega cube become 1, that become omega. So result is omega. So this particular set is also closed under multiplication. All the result are belongs to this particular set. Then closure property, the binary operation star is said to be a binary operation closed operation or a non-empty set A if A asterisk B must belongs to the set for all value of A and B. It means all pair of element of this set having the relation such that output product of these two elements by after performing the binary operation result must be belongs to the set only. That is the closure property. Is it closed? We have already calculated that it is closed. So, next associative property. Associative property suggests that let asterisk be a binary operation on a set and asterisk is said to be associative if A asterisk B asterisk C is equal to A asterisk B asterisk C. It means order doesn't matter for all A, B, C in the A. So, we check that this particular set under the multiplication is associative or not. So, we have to perform that A asterisk B asterisk C that must be equal to A asterisk B asterisk C. Put A is equal to 1, B is equal to I and C is equal to minus 1. A is equal to 1 that multiply, B is equal to I that multiplies, C is equal to minus 1 that must be equal to A, it means 1 that I that dot, then what is C? C is minus 1. After performing the binary operation I dot minus 1 that become minus I and minus I. What comes in right hand side? I dot 1 that become I, that minus 1 that become minus I. Left hand side is equal to right hand side. So, we can say that this particular set follow the associative property under the binary operation multiplication. Identity, then third property is identity property. For an algebraic system A is a set and asterisk is a binary operation. An element E must be in the set said to be an identity element if A asterisk A binary operation E that is equal to E binary operation A that must be equal to element itself for all value of A belongs to set A. So, we check that is there any identity element in this particular group or not. Here is the 1 is the identity element, E is equal to 1. Here is only 4 element. If we 1 dot 1 that become 1, minus 1 dot 1 that become minus 1, I dot 1 that become I and minus I dot 1 that become minus I. It means for all A asterisk E that equal to A. So, here 1 is the identity element and E must belongs to the set. Okay. So, here is the identity element is 1. If you want to observe a table, then what it is 1 minus 1 I and minus I. You can check this same sequence where is repeated is the same sequence. Same sequence is repeated here. So, 1 is the identity element. Okay. Then next inverse. For inverse, if A comma asterisk be the algebraic structure, then with identity element E, let A be the element in A and element B is said to be inverse of A if A asterisk B is equal to B asterisk A that equal to E. If we say that B is a inverse of A, so it means binary operation of element and its inverse that become to identity element E. It means we may write as A asterisk A inverse that equal to A inverse asterisk A that equal to E. So, here is 4 elements. So, what is the inverse of 1? What is the inverse of 1? Inverse of 1 is that 1 dot 1 ka inverse that must be the identity element and identity element is 1. So, 1 inverse is 1. What about minus 1 inverse? Minus 1 inverse is again minus 1. Minus 1 inverse is minus 1. if we multiply minus 1 dot minus 1, that become 1. So, minus 1 inverse is minus 1. What about I inverse? What about I inverse? What we have multiplied in I such that the result comes 1. What we can multiply? That is I dot minus I, that become minus I square become minus 1. So, minus minus plus, so it is equivalent to 1. So, I inverse is equal to I minus I. Okay. And what is minus I inverse? Minus I inverse is equal to I minus I multiplied by I, that become minus I square, that minus 1, then minus 1 1, again it is 1. So, we have the all elements have their inverse exist in the group. And second technique is the how to check that whether the particular element is the inverse of particular given element. What is the one inverse? One inverse is that it say that A multiplied by A inverse, that become E. So, you have to find out the identity element in this row. What is the identity element here? Identity element is 1 here. So, 1 inverse is 1 and minus 1, we check the identity element, that is 1. So, minus inverse is minus 1. Okay. Then what is the inverse of I? We find out the identity element, that is 1. So, I inverse is minus I, and what is minus I inverse? We find out the identity element, that is 1 here. So I minus I inverse is I. So, we can compute our table in such a way that we can easily calculate the what is the inverse of particular. And last property is commutative property. Commutative property says that let asterisk be the binary operation on a set A, then the binary operation said to be commutative if A asterisk B is equal to B asterisk A. It means if 1 plus 2 is equal to 2 plus 1, result become same. That is commutative property for all A and B. So, for this, if we check that this particular algebraic structure follow the commutative property or not, so we transpose this particular matrix. Transpose means row converted into column, column converted into row. This first row is same as first column, then second row same as second column, then third row is equivalent to third column, if fourth row is equivalent to fourth column. So, we can say that this particular algebraic structure follow the commutative property also. This particular algebraic structure follow all the property closed, associative, identity, inverse and commutative. So, we take some numerical portion, we check that if G is follow the all property or not. So, we multiply that 1 dot 1 is equal to 1 omega square, then omega square and omega की power 3, that become 1. Then omega square omega की power 3 again become 1, that is omega. Is it closed? Yes, it is closed because all elements belongs to this particular set. So, this is closed. Associative, we take 3 elements, that is 1 dot omega square. If both are equal, then we can say that it follow the associative property also. What is this 1 dot omega की power 3, omega की power 3, that become 1, that 1, and here that is omega dot omega square, that is omega की power 3, that become 1. So, left hand side is equal to right hand side. So, we can say that this particular algebraic structure is also follow the associative property under binary multiplication. Check this. Is there any identity element here? So, we check that ki, here we write that 1 omega and omega square, where it is repeated. Here it is repeated 1 omega and omega square. So identity element is 1. So E is equal to 1 here. And fourth property is inverse property. What is inverse property? So 1 inverse is, what is the 1 inverse? So we check that where is the identity element. 1 inverse is 1. And what is omega inverse? Where is the identity element? That is here. So omega inverse is omega square. And what about omega square inverse is, omega inverse is same omega. Okay. Then last property, that is commutative property. We transpose this, then what is come? 1 omega and omega square, first row, first column, then second row, second column, that omega square and 1, then third row and third column, third row and third column, that is omega square, 1 and omega. It is same as the matrix. So we can say that this particular algebraic structure also follow the all 5 properties, that is closure, associative, identity, inverse and commutative. So check this particular table also. Is this particular binary operation is closed? Where is the set is A comma B and binary operation is asterisk. What result is come? That is B. B belongs to the set, A also belongs to the set, A also belongs to the set and B also belongs to the set. So we can say that this is closed. This is closed, या फिर closure property is satisfied. Then second one, that is associative property. We take 3 elements of this particular set under this binary operation A, binary operation B, binary operation A, that must be equal to A binary operation B, binary operation A. What is B binary operation A? B binary operation A, that result is A. So A binary operation A. What is A binary operation A? A binary operation A, result is B. And here what is A binary operation B? A binary operation B, that become A. And A binary operation A binary operation A, that equal to B. So left hand side is equal to right hand side for all element of this particular set, or follow the associative property. So we can say that here associative property also satisfied. And third property is identity element. Is there any identity element? Either identity element is A or B. So we check that what is here is A and B, the same row is repeated here. So we can say that B is the identity element. E is equal to B. That third property is also satisfied. There is sub identity element in the group. And fourth property is inverse property. So we have to compute the A inverse. What is A inverse? We check the row and where is the identity element? Identity element. Okay, we erase some. Then we calculate. What is A inverse? That is, we check the identity element. Identity element is B here. So what is A inverse? A inverse is A. What is B inverse? What is B inverse? B inverse is B. So inverse property also satisfy. Can we check the commutative property? We transform our row into column. We transform our row into column. We write here A and B. We write here A and B. Here is the binary operation. Then first row is BA. So we put here BA. Then second row is AB. Then we write AB. And these both matrices are identical. So we can say that this is closure property, commutative property also satisfied for this particular algebraic structure. We can check here. Here is the plus 6 is the addition modulo 6. If we add two numbers like this, 5 modulo 6 addition with 3, then result will be the 8 mod 6. Then remainder, what is the remainder? If we divide 8 by 6, the remainder is 2. So 0 add with 0, result is 0. 0 add with 1, result is 1. 0 add with 2, result is 2. 0 add with 3, that result is 3. Then 0 add with 4, result is 4. Then 0 add with 5, that result is 5. Then 1 plus 0, 1, 2, 3, 4 and 5. Here is no problem. But 1 plus 5, that plus 5, that becomes 6, and mod 6 remainder will be 0. So we write here 0. Again 2 plus 0 become 2, 3, 4, 5. Then 2 plus 4, that becomes 6. 6 divided by 6, remainder is 0. So 0 here. Then 2 plus 5, 7. 7 divided by 6, result is 1. Okay. So similarly we fill all the tables elements, okay, in similar manner. So we can check that whether it is follow the all properties or not. Which property it is follow? Is it close? All the result belongs to this particular set only. Set is where, what is the set here? Set is 0, 1, 2, 3, 4 and 5. So all result belongs to this particular set only. So we can say that this particular plus 6 binary operation is closed under this particular set. And we check that is it associative. So we check that 1 plus 3 then plus 4, that also equal to 1 plus 3 plus 4. 1 plus 3 become 4, then 4 plus 4 become 8, and 8 mod 6, that become remainder is 2. And from right hand side 3 plus 4 become 7, 7 mod 6, that become 1, then 1 plus 1 become 2. So left hand side is equal to right hand side. So we can say that it is associative property is satisfied. Then third property is there is some identity element. To check here, what is here? That is 0, 1, 2, 3, 4 and 5. The same element is repeated in this row. So identity element is 0 here. So E is equal to 0 here. So identity property is also satisfied. So we calculate that is it follow the inverse property. So we compute the 0 inverse. So 0 inverse is that where is the identity element 0? 0 inverse is 0. Then what is 1 inverse? 1 inverse is where the identity element, that is 0. 1 inverse is 5. And what about 2 inverse? The 2 inverse is 4. Then what is 3 inverse? We check in the row of 3 that where is the identity element, that is 3. Then what is 4 inverse? That 4 inverse is, we check in the 4 row, that is 2. And what is 5 inverse? Then 5 inverse is, that is 1. All element of this particular set having their inverse exist in the set. So we can say that K inverse property is also satisfied. Then last property is commutative property. Commutative property, we check that this is the first row 0, 1, 2, 3, 4 and 5, 0, 1, 2, 3, 4, 5 which is equivalent, and we check that 1, 2, 3, 4, 5, 0. Then second row is equivalent to second column, third row is equivalent to third column, then fourth row is equivalent to fourth column and so on. So we can say that it is follow the commutative law also. So we can check for this also. Here binary asterisk 6 is the modulo multiplication 6. It means that if we multiply 4 by 6, that result become 24. We mod with 6, what is the remainder? Remainder is 0. So 4 multiplied by 6, that result is 0. If we multiply 0 with 0, that result become 0. Then if we 1 multiply by 0, 0, 1, 2, 3, 4 and 5. Then 2 multiply by 0, that is 0. Then 2, 4 and here is 6. 6 mod 6, remainder is 0. Then 4 into 2, that is 8. 8 mod 6, that become 2. Then 2 multiplied by 5, that become 10. 10 mod 6, that become 4. So here we all compute all the values of this particular algebraic structure. Is it closed? Yeah, it is closed. All value belongs to that particular set 0, 1, 2, 3, 4 and 5. It is associative? Yes, it is also associative. Calculate, is there any identity element here? So check that ki 0, 1, 2, 3 and 4 and same element is repeated here. So 1 is the identity element, that E is equal to 1. Is this algebraic structure inverse property also? We compute that ki 0, what is the 0 inverse? So we check the row 0. Here, where is the identity element? There is no identity element for the 0. So inverse property is not satisfied for this particular algebraic structure. कर दूं फिर स्टार्ट? अच्छा, वो एडिटिंग में कर लोगे? Okay. Now we discuss this particular few type of algebraic structure, that is semigroup, abelian semigroup, monoid, abelian monoid group and abelian group. Here is the set, and if we say that property number 1 and 2, that is closure and associative. If our algebraic structure follow the postulate 1 and property number 1 and 2, that is closure and associative, so it becomes semigroup. And monoid follow the property number 1, 2 and 3. Any algebraic structure which is closed, associative and identical is said to be monoid. Or what is group? Group is an algebraic structure which follow the property number 1, 2 and 3 and 4. It means it is closed, associative, there is some identity element and all element having their inverse exist. The word abelian means property number 5, that is commutative. If semigroup follow the property number 5, that is, it is said as a abelian semigroup. Means property number 1, 2 and 5. Monoid, it will follow the property number 1, 2 and 3.
इस स्लाइड को दोबारा से बोल देना सर, जहाँ से मतलब आपने ब्रेक लिया था तब से स्टार्ट कर।
अच्छा, now we discuss different type of algebraic structure. First one is the semigroup, which follow the two property, that is 1 and 2. One is the closure and second one is the associative property. And monoid follow three properties, property number 1, 2 and 3, that is closure, associative and identity. And group is a algebraic structure which follow the four property, that is closed, associative, identity and inverse. And word abelian means property number 5. Word abelian means property number 5, that is commutative. If semigroup is a commutative, follow the commutative property, so it will become abelian semigroup. It means property number 1, 2 and 5. And what is abelian monoid? Abelian monoid is a monoid which is commutative in nature. For monoid, it follow the property number 1, 2 and 3. And if it follow the property number 5, that is commutative, so it become abelian monoid. So we write here some definition of monoid. Monoid is an algebraic structure that is said to be monoid if the following conditions are satisfied. Strict is a closed operation, then strict is a associative operation, and there is an identity element in the G group. And what is group? Group is an algebraic structure, is said to be group if the following conditions are satisfied. First condition is closed, then associative, then identity, and then inverse. And what is abelian group? Abelian group, abelian word means property number 5, that is commutative. It means a algebraic structure which follow the commutative property, it is abelian. And group follow the 4 property, that is closure, associative, identity, and inverse. To show that this particular group, that is G1 and -1, is an abelian group under the multiplication. So we write here multiplication 1 dot 1 that become 1, then 1 dot -1 that become -1, and -1 dot 1 that is -1, and minus minus that is +1. Okay, is it closed? So all element belongs to this particular group, so we can say that it is closed. Then associative property, if we take 1 dot 1 dot -1, that is equal to 1 dot 1 dot -1, that result is -1, 1 dot -1 result is -1, 1 dot 1 that become 1, and that is -1. Left hand side is equal to right hand side. So we can say that this particular algebraic structure follow the associative property also. Is there any identity element? So we check that same element is repeated here. So we can say that 1 is the identity element, E is equal to 1. So identity property is also satisfied. So now we calculate the inverse property. Then what is the 1 inverse? Then we find out the identity element. 1 inverse become 1, that is equal to 1. And what about the -1 inverse? That -1 inverse is -1. So inverse element is also available in the group. So we can say that this particular is a group. And for the abelian group, abelian means property number 5, that is commutative in nature. So we transpose this, that is 1 and -1, and this is -1 and 1. So again the matrix is same as given. So we can say that it is also follow the commutative property. So we show that this particular set is abelian group under the multiplication. This is a practice question, that is again we check, we have already computed the modulo 7 for table for you. So we just check is it closed, all element belongs to this particular set, belongs to this particular set. So we can say that this is closed under this particular binary operation multiply modulo 7. Is there any identity element? Yes, here identity element is 1. What is the inverse? We check that identity element 1 inverse is 1. What is the 2 inverse? 2 inverse is 4. And what about the 3 inverse? 3 inverse is 5. 3 inverse is 5. And what is 4 inverse? 4 inverse is 2. And what is 5 inverse? 5 inverse is 3. And what about the 6 inverse? Then 6 inverse become 6. So inverse property also satisfied here. So we can say that this particular algebraic structure is group under binary operation multiplication modulo 7. So similarly you can solve this particular problem, that is 1 dot 1 that is 1, 1 dot 3 that become 3, then 1 dot 4 that become 4, then 1 dot 5 become 5, 1 dot 9 become 9. Then 3 dot 1 that become 3, 3 into 3 that is 9, and 3 into 4 that become 12, 12 divided by 11 remainder is 1. Then 3 into 5 that become 15, 15 mod 11 that become 4. Then 3 into 9 that become 27, that divide by 11, the result will be 5. So similarly you can compute and check whether it is follow the associative, commutative, identity, inverse, and all 5 property you can easily satisfy. Show that set of natural number n is a monoid with respect to multiplication. Monoid follow the 3 properties, that is closure, associative, and identity. There is some identity element in this particular set. So what is set? Set is 1, 2, 3 and up to infinite. So here the tabular method is not fulfill the all our requirement, all possible combination can be. So we use the hypothesis is for this, that closure. We know that the product of two natural number is again a natural number. We take any two numbers from this set, that 2.4 that equal to 8. Again natural product of two natural number is always a natural number. So we can say that the closure property is satisfied. For all element of this set belong A and B belongs to this particular natural set, the result must be belongs to this particular set. Here, so we can say that the multiplication is closed. What is associative? Associative means A dot B dot C that equal to A dot B dot C for all value A, B, C. We know that the matrix is always a associative in nature. Then identity element. So here one is the identity element is such that any element of this set multiplied by one result is element itself. So we can say that the identity property is also satisfied. So it means that this particular set is monoid under the binary operation multiplication. Okay, show that the set of all integer is a group with respect to addition. So what is our set? Set of all integer. Then closure property, we know that the sum of two integer is always a integer. So we can say that the addition of two element of this particular set must belongs to the Z. So associative property, we know that 1 plus 2 plus 3, that is result is always equal. So it means the binary operation plus is always associative in nature. So then third property, that is identity property. So identity property, here identity element is the 0. If we add any element with 0, then result is element itself. So 0 is the identity element. And what is the inverse? That A inverse is minus A. 2 become 2 addition with what element we result comes 0, that 2 add with minus 2, then A inverse is minus A and minus A inverse is A, and A must belongs to the Z. So inverse property is also satisfied. So we can say that the set of all integer is group with respect to addition. Thank you.